second lecture of this afternoon and second lectures of Tom. So please, when you are ready, you can start, Tom.
All right, I'm ready.
Okay.
So,
okay, thanks.
all right, hi everyone. So we continue with wormholes and the information paradox. So in the first lecture, we discussed two-dimensional dilaton gravity as a toy model for black holes, and in particular the RST model, where we're going to now be doing this calculation. In this lecture, well, we ended yesterday with this picture of an evaporating black hole. And as I said, what we're really interested in for the information paradox is the entropy of this radiation region R. But we're going to look at a slightly simpler example, and that's the information paradox for the eternal black hole. So now I want to describe how this goes. So recall that the eternal black hole in dilaton gravity is just ordinary Minkowski space, but where the dilaton hits its critical value. So we sort of delete these pieces of the space-time, and that's your eternal black hole. Now I'm going to take a region R, which has a piece over here, R1, and a piece over here, R2. And the region R is defined to be the union R1 and R2. And our goal will now be to calculate the entropy S of rho R. Now, I claim that this is very similar to the evaporating black hole. It's similar both physically and mathematically. Physically, well, as we'll see, this entropy appears to have an information paradox. It appears to violate unitarity. So the physics is very similar. The math is also very similar. One way to think about that is that if you go back to the evaporating black hole, then if you imagine calculating some correlation function, like with an operator inserted here, then you can, roughly speaking, you can calculate that by the method of images. There's a boundary. Since we're doing dilaton gravity, there's a boundary here in the space-time. So you can draw an image black hole over on the left and put an image point there. And that boundary can have some dynamics. So the final answer can be a little bit different, but as far as how it scales with time and the qualitative features, all of the one-sided physics of the evaporating black hole are very similar to the physics of the eternal black hole, where you just double everything. You just put all the images on the left-hand side. Okay, so we're going to do that with region R itself, and if we wanted to calculate correlation functions or something, we could do that with the correlation functions. Okay, we're going to do this two ways. First, we're going to do it using Hawking's calculation. Of course, he didn't actually look at this particular model, but I mean, using the way Hawking would have done it. And then we're going to include wormholes and islands and see how that changes the answer. Okay, so we're going to do this Hawking calculation pretty much from start to finish. So we have a lot of ground to cover, and let's jump right in. We'll start by calculating, well, I'm going to start by explaining how to calculate entropy in a conformal field theory in flat space-time. And the calculation we'll do is two-dimensional. A lot of these ideas carry over to higher dimensions, but the calculations become a lot more difficult. Okay, so the problem that we're starting with is that we have Minkowski space, two-dimensional Minkowski space. We have some interval A with endpoints x1 and x2. And we want to calculate the von Neumann entropy S of rho A. To do this, we're going to use the path integral and the replica method. The replica method is as follows. We first calculate the trace of rho r of a power, rho r to the n. And then we can extract the log if we can calculate this for all n. So the motivation for doing this is just that logs are hard. But well, let me write the formula again. So this is minus trace. The thing we're trying to calculate is minus trace of rho log rho. That's the log of an operator. Okay, so that is a very complicated thing, and it's easier to deal with powers. Okay, especially when you're doing path integrals. So that's why we're using the replica method. I'm going to define this with the unnormalized density matrix here, which means that that's just a choice. It's convenient, but that means that the von Neumann entropy is minus trace of the normalized density matrix rho log rho. So I'll put a hat on those to denote that they're normalized. Rho A hat is rho A over trace rho A. Okay, I see there's something going into the chat, but I'm not going to monitor it because it's confusing.
Okay, yeah, there is one question in the chat from Igor. Igor, do you want to ask the question?
Yes, I can read. It's just a quick conceptual question. In the Kruskal maximal extension that you are using, are you thinking about the regions 1 and 2 as being different spacetimes connected by an Einstein-Rosen bridge, or the same spacetime, however, each patch 1 and 2 describing regions asymptotically far away from each other?
Those two things are really equivalent. So I guess you're going back to this picture here.
Yes.
Those are not really two different things that you just said. Those are just two ways of thinking about the same picture, and you can think about it either way. It's okay. The eternal black hole is a single spacetime with two asymptotic regions. Now in this picture, I'm just talking about flat space. We're not doing black holes at this point, but we're going to come back to the black hole in a minute. Well, not in a minute, in a few minutes. Okay, so the point of the replica method is that if we can calculate these replica partition functions, Zn, then formally we can write the von Neumann entropy as 1 minus n dn of log z of n at n equals 1. Now, to make sense of this, you have to be able to analytically continue to non-integer n. When we talk about these replicas, we're going to replicate the physical system with some auxiliary systems. We're going to replicate an integer number of times. But the trick is we're going to find a way of calculating calculating z at non-integer n. We're going to analytically continue in n, and then use this to extract the von Neumann entropy. So our task now is to find a way of writing this quantity as a path integral. So let me first remind you of a couple things about Euclidean path integrals in quantum field theory. The first is that the vacuum state from the Euclidean path integral is the path integral on the half space Euclidean time less than 0. What I mean by that is that the ground state wave functional which is by definition the overlap of the ground state with some field data phi naught, is calculated by the path integral that I'm going to draw as follows. So this is Euclidean time. So this is in 2 dimensions. This is the lower half plane. More generally, it would be a Euclidean half space. So this is Euclidean time 0, and we put a boundary condition on this dashed line, which is phi naught of x, and then we do the path integral on this half space. This calculates the ground state wave function. Remember, the reason for this is that no matter what junk we put way down here at the bottom of the path integral, this evolving in Euclidean time is an action by e to the minus te times the Hamiltonian. So no matter what you put down at the bottom, only this evolution in Euclidean time will project onto the vacuum state. Okay, so this is our vacuum, and so when we think about the density matrix for the vacuum, which is just 0, 0, I like to think about that as a path integral that looks like this. Where the bottom thing here is the bra or the ket. I can't remember which is which, and the other one's a ket. Okay, so the way to think about this picture is now on the left-hand side we have an operator, and on the right-hand side we have 2 open cuts. So a path integral with an open cut is a linear operator, where you should think of these as like unspecified boundary conditions. And this is, if this is confusing, you should just think about matrix elements. So like phi naught of x, rho vac, phi naught prime of x would be the path integral where you now supply the boundary condition phi naught, or phi naught and phi naught prime, to those open cuts. But I prefer not to put in the field data, and just to think of this as the path integral that defines an operator. Is that picture clear? Does anyone want to pause me and ask a question about this picture?
Yeah.
So here we have a path integral without any boundary conditions.
Well, you can't, this is a formal statement. It's like an indefinite integral where I haven't specified the boundary condition. What it means is that you should think of an indefinite integral as a linear functional on boundary conditions. And so the open slots, the open places where you can now supply a boundary condition, those are the open slots of this operator, the thing that the operator acts on.
I see. So if you put some field values phi I, phi j, that just those are the boundary conditions. So just vary phi I, phi j, and that will give you the different sort of path integral or the matrix elements of this object on the left, right?
That's right. That's right.
Okay.
So the matrix elements are given by this path integral with some specified boundary conditions. The operator itself is the path integral without anything specified. So it's an operator. Okay, so the advantage of writing things this way is that I can now talk about row A in vacuum. Okay, so row A is by definition the trace over a complement of row vac. This is the reduced density matrix on region A. So the definition of the reduced density matrix is that you sum over states n on a complement of n row vac n. If we write this now as a path integral, what does this say? So let's put in our row vac. So that looked like this. Now we need to specify region A. So let's say region A is here. And now what we need to do is to sum over, we need to calculate these matrix elements where we only specify the field data on a complement. Okay, so the way we're going to do that is to sum over n of some data, some field data here, and here, and here, and here. So what I've drawn is a path integral representation of this expression here, where now the boundary conditions on region A are open, unspecified. So this picture is still an operator on region A, but on region A complement, I've now done the trace. I'm specifying the boundary conditions and doing the trace. Okay, so this is an operator. This expression is an operator on region A, but not on the complement. We've traced that out. Now the last step here is to notice that here we're putting the same boundary conditions on the top part and the bottom part, and then we're summing over them. Well, putting some field data at these two spots and then summing over all possible field configurations in that spot is the same as just erasing that cut altogether. Okay, so I can redraw this. And we have row A is now the path integral it looks like this. Okay, so what's happened here is we took that field data, we were summing over field data here, but it was the same on top and bottom. So that has the effect of just gluing the manifold together. That's the same as saying all fields are just smoothly matched across top to bottom. So we've glued the top sheet to the bottom sheet. Same thing over here. We have not glued along region A. Okay, so region A has two open cuts, which are at the top and bottom of of this branch cut that I've drawn. So you should think of this expression as being a shorthand for the matrix elements, phi prime rho A. Phi is the path integral with this cut, and you specify the field data phi prime on top and phi on bottom. Okay, so this very last picture is a number. This is a number. All the other pictures that I've drawn were pictures for operators because they were open cuts. Okay. So
I have a question.
Yes.
So when you give field data in this region A, like what kind of boundary condition do you put at the edge of the cuts?
That is, yeah. So the question is, what do we do about these points here? And the answer is that those points are singular, and we're going to need to deal with them by some prescription. So, for example, probably the simplest thing to do is to actually put a little circle here and to put a little circle here and to impose some boundary condition on that circle and then take the circles to 0. And when we do the calculations that we're going to do, there's some divergence coming from that. And you want to make sure that you basically need to renormalize. You want to make sure that you only keep track of the scheme independent part, and we'll see these divergences coming up in the calculation that we're about to do. That's where the divergence in the entanglement entropy will come from. Okay, are there any other questions about? So this was the key picture that I wanted to explain. Are there any questions about that picture? Other questions? Okay, so we can now write down the path integral for the replica partition function. So we're going to need a new page for this one. Let's see. So here it is. Trace of rho A to the n. So we just draw n copies of rho A. There's 1. There's 2. Dot, dot, dot. And copy n. Each of these has 2 open cuts. But what we want to do is we want to do matrix multiplication on. So we have these operators, our big matrices. Think of them as big matrices that we're multiplying together. Okay, so the effect of that matrix multiplication is to glue these cuts together. So we glue the top of this cut to the bottom of this cut. And similarly, we glue the top of this one to the bottom of the next one. And we glue the top of this last cut back to the bottom of the first cut. That's the fact that it's a trace. So we glue all the way around. So you should think of this gluing. By gluing manifolds, I just mean you identify everything at the 2 points. So like fields are continuous, for example. And you should think about this as like, if you're walking along on this manifold and you walk through this way, you'll come out down here. And if you're walking through here, you're going to come out on the 3rd sheet, and so on. So these are glued together across these branch cuts. The gluing is matrix multiplication.
Don, I think there is a question from Kat.
Yes.
Is the n inside the trace?
Yes, the n is inside the trace. Yeah, thanks. Okay, so gluing is matrix multiplication. Like if we have row A times row A, then we're just inserting a complete set of states in there, and calculating row A, phi n, row A. But summing over that field data on the cut has exactly this effect of gluing together the manifolds, just as we saw in the simpler example a couple minutes ago. There's another question, Pablo?
Yes.
Yes, just real quick to the order in which you glue everything together. So how do I intuitively know which one is the right order? So how do I know that I'm not supposed to, for example, glue the upper bound with of the first copy with the upper bound of the second copy instead of the lower one?
Good. So that's just dictated by the multiplication. Okay. So we're doing this trace is the sum over n1. Well, sum over ni, let's say, of n1 row A, n2 row A, n3 ... And so we can see in this expression that the field data for the right slot of this first copy is identical to the field data on the left slot of the next copy. Okay, and the top of this manifold is like the left slot. Sorry, the top of the cut is the left slot of the operator. The bottom of the cut is the right slot of the operator. When you translate it in terms of matrix elements, that was this expression. Let's see. I'm using this formula here. So that tells us how to do the gluing. And sometimes you see more elaborate gluings, like when people talk about, for example, the entanglement negativity, there's some partial transpose involved that changes the way you do this gluing. And all that can be handled by just writing out the matrix multiplication that you're trying to achieve with your gluing. Okay. So there's one comment that I want to make here, which we'll come back to in a little bit. Let me just make it here and note it for further reference. If we look at one of these, so these things these things are sometimes called twist insertions or twist points or twist operators. It just means the branch point on this branch cover. So what I want to point out is that the metric around this point is dz bar. That's because we're not doing gravity at this point. We're just doing conformal field theory, and at no point did we change the metric. We're doing conformal field theory in flat space. So the metric is dz bar, but the identification, let's call this point Z2 here. The identification around this point Z2 is that you have to go around the point n times to get back to where you started. If you just go around once, so like if I sit here and I just go once around, I'm going to find myself up here on sheet 1. If I start here and I go around n times, then I'll get back to where I started. What this means is that there's actually a singularity here. There's a conical excess singularity at the branch point or the twist point. Okay, so we're actually not talking here about a smooth manifold. We're talking about doing the path integral on a singular manifold with this conical excess. Okay. So this is the path integral that we want to do. Now we're going to evaluate this path integral. I'm just going to sketch this calculation. I'm going to give you enough information that you can reconstruct the full calculation in one page later, but I don't want to spend too much time in the algebra. So I'm just going to give you enough information to repeat this calculation yourself, and I encourage you to do so afterward. The first step in this calculation is to map from, okay, so let's call this coordinate z. There's a z coordinate on each of these planes. Okay, so now we're going to map from z to w with the mapping w is equal to z minus z1 over z2 minus z to the 1 over n. And what I claim is that that just maps this entire manifold to the w plane. In other words, w is a global coordinate on this multi-sheeted cover of the z plane. If you look at this expression here, if you focus in the vicinity of one of these branch points, like z1, you can see how that's working. That clearly from this expression, you have to go, if you go n times around z1, then you'll just go around the w plane once. Okay, so roughly what's happening here is that the w plane has a bunch of wedges on it, and these correspond to the n sheets of the z plane. Now, the advantage of doing this is that we're doing conformal field theory, and in conformal field theory, we know that the stress tensor vanishes on the plane. Okay, so the stress tensor, the expectation value of the stress tensor on the w plane is therefore 0. Now we can map back to the z plane, and now to calculate t of z, we just use the anomalous transformation law for the stress tensor, which says that t of z is minus c over 24 pi times the Schwartzian derivative w comma z. This is easy to calculate. I'm not going to go through the algebra, but you just plug in this w to calculate your Schwartzian derivative. Next, we're going to use the word identity in the form d z1 log zn is equal, well, it's proportional, I won't try to get the factors right, it's proportional to the residue at z near z1 of t of z. If you work through the algebra and the Schwartzian derivatives, what you'll find is that this is 1 minus 1 over n squared times 1 over z1 minus z2. Now we can simply integrate to calculate log z, or z, and the answer that gives is Zn is Z1 minus Z2 to minus 2 delta n, where delta n is defined to be C over 12 times n minus 1 over n. So this is the answer to the this is the calculation of the replica partition function. This is the partition function of a CFT on this crazy looking manifold that we're interested in here. And what I've just described here is a calculation of Carty and Calabrese. Actually, the formula, the final answer goes back earlier to earlier papers, but the way I've done the calculation is following Carty and Calabrese. A comment is that sometimes people call this the twist correlator, sigma plus of Z1, sigma minus of Z2. And the reason is that this looks like a two-point function, right? This expression here looks like the two-point function of primary operators in a conformal field theory, just as a power law. So you can think of this as defining an operator. This is not really as deep as it sounds. Just think of this as the definition of the twist correlation function. It's useful to think about this way because we're used to thinking about correlation functions. We know how to deal with their ward identities. And this is just basically a reminder to ourselves that this object obeys all the same ward identities as a two-point function. Okay, so that's the calculation of the replica partition function. Sorry, there's a question here?
Yeah, there is a question. Maybe George, if you want to.
Yeah, go ahead.
Go ahead.
Yeah, is there just an obvious way why these should be twist fields? Like, rather than just, I mean, this looks like naively any correlator. Is there a reason why this says, oh, this should look
This is the definition of a twist field. So there isn't really a deep reason. It's just, that's just what it's called. You should think of this as defining the operator sigma. Okay. So that's our replica partition function. We can now calculate the entropy. Now you'll notice here that this function we started with n being an integer, but this function we ended up with, it doesn't care if n is an integer or not. So we can calculate 1 minus n dn log zn, and that's going to give the entropy. Well, when we take n to 1, that gives the entropy. And you just take this formula that we have and you find the entropy S is equal to C over 3 times log of Z1 minus Z2 over epsilon. And let me make a comment about that epsilon, which is the only thing that is not determined by this calculation. So that epsilon is an arbitrary constant that can be added. And you should think of that as a UV divergence. Okay, so there's a problem with the calculation that I just described, which is that it was a partition function on a singular manifold. That doesn't really make sense. Okay, so what you really need to do is you need to cut out a little circle around the twist point, remove that from the manifold, do the whole calculation on this regulated manifold, and then this is the answer that you get, where epsilon is the size of the circle that you cut out. Now, that term is non-universal, but since it shows up in a log, well, in general, it might be non-universal, but since it's showing up in a log, there's a physical contribution here, which is independent of the regulations.
I have a question.
Yes.
So if I want a coordinate of 3 twist fields, by which I mean inserting 3 cuts and 1 cut till infinity or something, does the coordinator come out as per the usual rules of CFT 3-point functions with these dimensions?
Well, I couldn't entirely hear. The audio is not very good, but I think you're asking about 3 points. And
yeah, 3 points, and where I interpret 2 of them joining and 1 cut extending to infinity or something, and then can I get the 3-point function using usual 3-point function formula, but with this delta?
Well, first of all, the 3-point function is 0 because, well, if you think about that in terms of partition functions, it's because there's no way to have 3 branch points. There's nowhere for the other branch cut to end. If you think about it in terms of operators, then you should think of these operators as being charged. One has charge +1 and the other has charge minus, and only neutral correlators will be non-zero. You can calculate a 4-point function of twist operators, and that would correspond to the entanglement entropy of a union of 2 regions. Those 4-point functions do obey the Ward identities of a 4-point function.
Just as a light curiosity, do people try to bootstrap such things directly?
Well, people have certainly used a lot of bootstrappy methods, say for calculating entanglement entropies, like conformal block expansions, that sort of thing. If you're asking more about like numerical bootstrap, then I think the answer is that I think the answer is no. I can't think of anyone who's really set up that as a way of as a computational method for trying to solve CFTs. It might be an interesting thing to try.
Thank you.
Okay, so that's the answer to this CFT entanglement entropy in flat space. Now, we're actually interested not in flat space, but in conformally flat space. So we want to look at the metric e to the 2 rho dz bar. Fortunately, we know how to do a Vial transformation on a conformal correlator. This thing is just acting like a 2-point function. So what happens is that this sigma plus of Z1, sigma minus of Z2 just gets Vial transformed. And the Vial transformation is just e to the minus e to the minus delta n times rho of Z1 plus rho of Z2. So there's a contribution from each operator insertion, and it's raised to the power of the scaling dimension. And that's it. That's all we have to do to calculate the entanglement entropy in curved space. If we turn this into a statement about the entanglement entropy, then we could write it this way. S is then C over 6 log Z1 minus Z1 bar, sorry, Z1 minus Z2, that should say, Z1 bar minus Z2 bar over epsilon squared, the UV cutoff, times e to the minus rho of Z1 minus rho of Z2. And this is the formula for the entanglement entropy of a CFT in curved space. we just derived this formula in Euclidean signature, but the same formula is true in Lorentzian signature. All we need to do is analytically continue. What that means in practice is that you just use literally the same formula, but you take z and z bar to be independent real numbers instead of complex conjugates. If you do that, then you're talking about points in Minkowski space. Okay. This has been a sort of detour into the discussion of calculating entanglement entropy in CFT and curved space. But now we can come back to our eternal black hole. So let's draw that picture again. We have our region R. We have our singularities. We have region R, which is this union of these two regions over here. And what we would like to do, let's give these endpoints names. So we'll call them x1 and x2. This is the same coordinates x minus and x plus that I was using yesterday. Now we want to calculate S of rho R. Well, Hawking's calculation of the entropy and the classic calculation of the entropy of Hawking radiation is to simply apply the formula that we just derived to this spacetime. That's the classic prescription of QFT in curved space, is you just think about quantum fields in this semi-classical background, and you treat their dynamics and their density matrix and everything else as just the dynamics of a quantum field theory on this background. Now, the fields can backreact. The fields can cause the metric to backreact, but once you solve for that backreaction, the classic way of doing this calculation is then just to treat it as essentially quantum field theory in curved space. So that's how we're going to do the calculation first, and that's what's going to get us into trouble. Okay, we can immediately use our formula from the last half hour to do this calculation. Rho sub R, I mean, R is a disjoint, R has two disjoint regions, but the complement region, A, is exactly like the A that we've been talking about. Okay, so the classic calculation is as follows. S of rho R is equal to S of rho A, because the quantum fields are pure on the full Cauchy slice. Then we just plug in our formula that we just derived. So this is n over 6. I'm talking about n free fields as in the RST model. So the central charge is n log minus x2 plus minus x1 plus x2 minus x1 minus over epsilon squared e to the minus rho of x1 minus rho of x2. I've just plugged in the formula that we just derived in Lorentzian notation now. To get some intuition for what this formula is telling us, I want to take x1 and x2 up to scri plus. That is, on this picture, I'm imagining that there's some observer very far away from the black hole who's collecting the Hawking radiation. So we take this point up near scri plus. And I'm also going to take x1 to be x2 reflected. Okay, so I'll just take these points symmetrically up towards scribe plus, as drawn in the picture. Finally, I'm going to write this in terms of the Minkowski, in terms of the Schwarzschild coordinates, which I discussed yesterday. These are related to the x coordinates by x plus minus is equal to plus minus e to the plus minus t plus minus x. Good. Okay. So with all that set up, I'm now just going to plug into this formula. I'm not going to do the algebra and take the limits for you. You can work that through that yourself. But here's what you should get. S of rho r. Let me call this S Q of t of rho r to emphasize that this is by the ordinary methods of semi-classical gravity and Q of t is equal to n over 3 times t2 plus an infinite constant. And I'll make this an exercise. I've given you everything you need to rederive this formula. Okay, now we're at the information paradox. Okay, so the thing to notice here is that this is growing linearly in time. So what this means is that if you stand outside the black hole and you collect this Hawking radiation, the entropy of the radiation that you collect just grows linearly forever without bound. Okay, so the paradox is that S goes to infinity. Why is it a paradox? Because the black hole has finite entropy if it's a unitary system made up of some quantum mechanical degrees of freedom. Okay, so we have ourselves an information paradox. It's very similar, it's essentially the same as the usual information paradox, but in the context of this eternal black hole. Now I want to sharpen this a bit. And this is where we get into the page curve. So the sharper version of the paradox is to make this quantitative. Okay, infinity is clearly bad. Infinity is clearly a problem. But when do we really have a problem? There's some finite threshold where we've violated unitarity. So I want to explain what that is. So I have to draw yet another diagram. Okay. Here's our black hole. So here's region R. So when do we have a problem? The paradox is when S of rho r exceeds the generalized entropy of R complement. Let me explain that. So R complement is everything else in this space-time. And R complement is what the radiation is entangled with. So we can't have more, the entropy of these two regions have to be equal to each other. Now, the generalized entropy is not quite the same as the von Neumann entropy. The generalized entropy is what we think of as a coarse-grained entropy counting the available degrees of freedom. But a coarse-grained entropy is always larger than a fine-grained entropy. Okay, so think of the right-hand side as counting degrees of freedom that R can entangle with. And then the left-hand side is the entropy. Okay, so you can't have more entropy than the degrees of freedom you can entangle with. Now I can plot the page curve for this problem. So we'll look at, as a function of time, we'll look at the entropy. So let's first plot the linearly growing entropy that we just calculated. That's like Hawking's calculation, so I'll call that S Hawking, that just grows as n/3 times t. That's Hawking's calculation. And what we want to do is we want to compare that to the generalized entropy of R complement. So this is S gen of R complement. And that's just a constant, okay, as I've drawn it. The exact formula for it is twice the entropy of the black hole plus n/3 times the distance that we are from the black hole, x2, plus the same infinite constant as we got in our calculation of the Hawking radiation. I can come back and explain this formula in a minute in a little bit more detail if you want, but let me just give the basic picture, explain the basic picture of the page curve now. So the point is that this region that we're entangled with has a maximal entropy, which is S gen. So when we exceed that entropy in the radiation, that's where we have a problem. So this generalized entropy is giving us an upper bound consistent with unitarity. And so at this early time, as we start to collect the radiation, there's no problem. We're just, the radiation, the entropy is going up. But as soon as we get to here, we start to, if we follow this curve any further, we're going to violate unitarity. So the prediction of Don Page was that actually the true curve should follow like this. So that's the Page curve for the eternal black hole. I drew the Page curve yesterday for the evaporating black hole. This is very similar, except instead of going back down, it's bounded by this constant because the black hole never evaporates away, so there's no reason it would have to go back down to 0. There's the thing I didn't explain yet is this S black hole. So S black hole means area over 4, just the usual Bekenstein-Hawking entropy of a black hole, except with a caveat that in the area really means the dilaton when you're doing two-dimensional dilaton gravity. And this black hole entropy is just n/6 times the mass of the black hole in the RST model. So the way to understand this generalized entropy formula is as follows. We're doing an eternal black hole. So the generalized entropy has a contribution from each side of the black hole. So that's this 2s black hole. This term here is the entropy of the quantum fields outside the black hole, but not in region R. So this is the contribution from the quantum fields outside the horizon. This infinite constant is the UV divergence coming from the border, the edge, between region R and its complement. That's why it's the same infinite constant on the two sides of this inequality. That is, the UV divergence in region R is exactly equal to the UV divergence in the generalized entropy. And that's important here because remember the paradox is when these two lines cross. So we do have to be careful about first subtracting off those UV divergences and then comparing the two sides. If the UV divergence didn't match, then we wouldn't be able to make this comparison. Okay, there's a question. Lucas?
Yeah, I have a question. So the G Newton is renormalized. I mean, it's a bare complement or it's a renormalized complement. I'm wondering if G Newton also contributes with this infinite part, and then spell your argument that the divergent part is equal for the field for the region R and the outside R plus black hole.
I can only half hear because I'm not sure if it's my audio or what, but you're asking about Newton. So okay, so the way we've taken the large N limit here is that you should think of G Newton as scaling with 1 over N. Okay, so the leading order at large N is, we're keeping everything to leading order at large N with the scaling G Newton as 1 over N. I don't know if that answered your question because I'm not sure what the question was.
Yeah, no, sorry. So the question is, I'm wondering if the G Newton receive corrections, anomalous corrections. I was thinking like in quantum electrodynamics, the complement constant receive group corrections, so get normalized.
You're asking about the corrections to G Newton. Good. Okay, so yeah, let me explain that. So when we calculate the generalized entropy of this region, it has two contributions. It has a contribution from the area of the horizon at these 2 points. That has a 1 over G Newton. So let me write a formula. So S gen of our complement is the sum of a quarter the area of the horizons in our complement. So that's those two spots. And then there's a S CFT of what I'll call region B. Okay, so region B is the union of these two segments here. That is, it's the region, it's the quantum fields outside the horizon of the black hole. Okay, so that's the generalized entropy. Now, here's where the renormalization of Newton's constant enters. There's a 1 over G Newton in the area term, and there's a UV divergence from the horizon in this matter entropy of region B. Those two things cancel completely. Okay, so the renormalization of Newton's constant cancels against the UV divergence from the matter entropy, and when expressed in terms of the normalized Newton's constant, the generalized entropy never has infinite contributions from the horizon. The generalized entropy does have an infinite contribution from this point out here, which is the boundary of region R, but that infinite contribution is no problem because that's exactly the same infinite contribution that we had in our calculation of the Hawking radiation. Okay, it was a long-winded answer, but I hope it answered your question. There was somebody else with a hand up. Ishu?
Oh yeah, so maybe I was mistaken, but it seems to me like when you described the methods of calculating the entropy of the R, the replica method, it seems to me you are calculating an entropy of a stationary state or static state. Is it true?
Yes, that's right. So in doing this Euclidean path integral, we're looking at a state with a killing vector, and the eternal black hole does have a killing vector. It has a killing vector. There's a killing vector where time goes up in the right and time goes down on the left. Okay, so that's a killing symmetry of this space-time. The reason we're getting something time dependent is because we took the region R to go up on both sides.
Oh, I see.
If we had taken one to go up and the other to go down, that would be on isometry and everything would be time independent.
Yeah. I see. Thanks a lot. That solved my puzzle exactly. Thank you.
Akhil?
Hi, so the S-gen arc complement doesn't include the entropy of fields inside the horizon, is it?
No, it does not. Okay,
and why is that an intuitive thing?
Did you say why is that the important thing?
Yeah, I mean, what hints that's the right thing? Yeah.
Well, that's kind of, that's a matter of where we see the problem, where we see the paradox. So if we just talked about the entropy of the fields in our complement, then there would be no problem. The problem is that the entropy of the fields in our complement can be arbitrarily large. Okay, so if we go to late times here, there's this Einstein-Rosen bridge across the inside of the black hole. That's growing linearly in time. Okay, so the Einstein-Rosen bridge is getting huge and seems to be able to accommodate arbitrarily large entropy in the quantum fields on that slice. But that's the paradox. See, the paradox is that we think that black holes have a finite number of degrees of freedom given by area over 4. Well, there's different versions of the paradox here, but for these purposes, we think that they have a finite number of degrees of freedom, area over 4, and just the fact that there's a lot of matter in that slice doesn't change that. We still think that there's just some quantum mechanical system with some degrees of freedom, and so that's really the issue. Now, the paradox is sharper for an evaporating black hole, because for an evaporating black hole, we never have to make this assumption about the entropy being area over 4. We just have to say that the black hole has 0 entropy at the end of the day. For the eternal black hole, all we need in order to say that there's a paradox is to say that the Hilbert space of the black hole, or the degrees of freedom of the black hole, are finite. Then we can always go to late times that are, so it's so late that the entropy is arbitrarily large, and it can't possibly come from entanglement with the black hole degrees of freedom.
So do you add additional boundary terms because you're cutting off the complement at the horizon?
Right? By boundary terms, do you mean this area term?
Yeah, the diverging term, yes.
No, I wouldn't say that's why we're adding them. I would say that we're adding them because
No, I asked, do you add them like extra terms? But because these boundaries were not specified in the original problem, right?
no, we don't add anything else. This is the definition of the generalized entropy. And the reason we're using this definition is because this is the thing that obeys the laws of thermodynamics, like that were derived by Bekenstein and Christodoulou and others back in the 70s. So this is the thing that appears to obey the laws of thermodynamics. It increases in time. It obeys the first law and everything. So this is the thing that we think is supposed to count the microscopic entropy of the black hole. And that's what we're using to look for a problem. We don't add any other terms. This is just the definition. Okay, I think we're done for today unless there are other questions.
Yes. Are there other questions, or so we can thank Tom for the lecture. If you can unmute your or use the reaction of the Zoom. So please, if there are any other questions, and